Welcome to Chapter 7. In Chapter 7 we're going to be looking at transportation problems. So in the transportation problem, you can imagine that that is very applied, especially right now when stores are trying to make all their, they're trying to fill their shelves. And so let's just take a look at a real basic problem here. Suppose that I have a shipping company and I have two warehouses. I'll just call them W's for the two warehouses, and they're shipping goods to three customers, so we'll just say three C's. And our two warehouses each have the ability, or they can ship 50 units, you can say, each out to the customers, and the customers have a certain demand. And so let's say that actually let's not make that equal, just to make that not symmetric. For our example, 50 and 40, and then for the three customers, each customer wants 30 units. Okay, and so what we're going to do is assume costs are associated with shipping one unit from warehouse I to customer J. Okay, and so what should my decision variables be? It looks like my decision variables, it's probably easiest to go ahead and write our decision variables in two dimensions here, or two subscripts. Xij be the amount shipped, oops, let me see if I can spell, shipped from warehouse I to customer J. Okay, and so then you can kind of see, let's see, I'm using C's for customers. I probably should have used C's for my costs. Well, if you see a C with a double subscript, it's a cost, okay? Okay, so then what is my cost, or what is my linear program here? That's what I'm trying to say. This is a linear programming problem. So what is it that we want to minimize? We want to minimize your shipping cost. And so that's going to be a minimize Z equals, let's say C11 is the cost from warehouse 1 to customer 1, X11 plus C12 X12 plus C13 X13 plus C21 times X21 plus C22 X22 plus C23 X23. Okay, so those are all my variables now. I've got 6 of them. And now what are my constraints? Subject to, well, I want the entire shipment from warehouse 1 needs to be 50 or less, right? And so going from warehouse 1 means the first index of our double subscript is 1, so that means X11 plus X12 plus X13. That's everything shipping from warehouse 1. That should be less than or equal to 50, right? Similarly for warehouse 2, so let's just say warehouse 1 there. Warehouse 2 is X21 plus X22 plus X23 should be less than or equal to 40. Okay, warehouse 2. Now customer 1 doesn't want any less than 30 units, right, if the demand is 30. So therefore, what gets shipped to customer 1 would be X11 plus X21, right? And so that's shipping from warehouse 1 to customer 1, from warehouse 2 to customer 1. That should be, greater than or equal to 30. Okay, so similarly, X21 plus X22 is greater than or equal to 30. And then, yes, that's, wait a minute. This is going to customer 1. That's not right. This is from warehouse 2 to customer I want to go to from warehouse 2. I want to go from warehouse 1 first. Warehouse 1 to customer 2. There we go. Then from warehouse 2 to customer 2. Good. Greater than or equal to 30. Finally, 1, 3 plus, there we go, 2, 3. Had a little brain freeze there. C1, C2, C3. Good. Okay. There is our linear programming. So it's ready to go. Now, we could just go ahead and solve this using any of our techniques, simplex method, but you'll notice that there's a lot of variables to keep track of here. And actually, there's a more simple technique that we can use that we want to examine, and that technique is called a transportation tableau. And so let's go ahead and write this as a transportation tableau. The transportation tableau. The idea is that in a transportation tableau or a transportation problem, you always have warehouses shipping to customers or something that you can map to that. You can say that there's sources going to sinks, if you'd like, sources being warehouses, sinks being customers. And so in this case, we can build a table where the warehouses are on one side, warehouses. I'm not going to fit that in there. Warehouses. Okay. And then on this side, we're going to put our customers. And so we're just going to be building a table. Let's just see how it looks. We won't go into the general case. So let's say warehouse 1, warehouse 2, and then customer 1, customer 2, customer 3. Okay, and then in this tableau, we're going to mark off our values here. And so this is going to be our total for warehouse 1 is 50, 40, and then the demand was 30 for each of our customers. And then what I'm going to do is I'm going to put the costs in a little box in the corner here. Okay. The reason being that I want to save this area, these areas, for how much is going from warehouse I to customer J. Okay, so leave these spots open for now, and those are what we're going to fill in with numbers. And in fact, this would be our x11, right? x12, x13, x21, x22, x23. And so you can see here what we were doing with our linear program, right? We were summing across and across for 2 of the constraints, and then the other constraints was summing down, sum down, sum down. Okay, and now I've made a big mess out of my Tableau. See if we can get rid of it. Whoops, I'm getting rid of too much. Okay. It'll only take a second to get it back. Okay. So, let's go ahead and reset this. One of these days I'm going to learn how to do this well. Okay. So now we have our costs. So I'm going to go ahead and fill them in, even though we're not really going to use them for right now, just so you can kind of see what this looks like. 35, 50, 25. These would have to be given to you, right, as your costs. Good. Okay, and so this is what a transportation tableau looks like. Okay, and again, the solution to a transportation tableau would be filling in these blanks in order to match the constraints. Okay. Now it looks like we're just about to the 10-minute mark, so I may stop there. I hate to break this up too much, but the next video we're going to see, you'll notice that something kind of nice happened in this tableau, and that is the total demand in this case is 90 and the total supply is 90, and so what happens? 90 equals 90. If that happens, this is called a balanced transportation problem. And so what you might imagine is going to happen, what happens if we try to solve a problem that is unbalanced. Okay, and so that's the next video. Stay tuned for that.